Hey, AP Chemsters, this is Mrs. Bailey bringing you section 5.9 blank wall. This is the mean free path diffusion and effusion of gases. If you recall, section 5.8 was the kinetic molecular theory. We're talking about on the molecular level, about pressures being collisions and temperatures related to kinetic energy, and volume is how much space things take up. In the second half of that, we're talking more about the root mean square and the average velocity, and how the average velocity is dependent on the molar mass, but the average kinetic energy is only dependent on the temperature, the Kelvin temperature. So this, we're still talking about molecular motion of gases, okay? So that's what this whole thing is about here. And so let's talk about effusion versus diffusion. Effusion is closely related to that. Diffusion is a term used describing the mixing of gases. So if I have two holes in one container, and let's say on the one side I have some hydrogen and the other side I have some oxygen, and I squirt some in both, how do they mix? Okay, and you know what? That is a really complicated thing to calculate. It is well beyond the scope of AP Chemistry's calculations. So effusion is a term used to describe the passage of a single gas through a tiny hole into an evacuated. There's nothing else in there, chamber shown below. So the rate of effusion measures the speed at which the gas is transferred into the chamber. So we can use this as, let's say, a quantity. So how many gas molecules per time, okay? It is not necessarily just like 3 seconds or 10 seconds or whatever. It's, you know, how many per second you could, or something along those lines, okay? So let's see here. Scroll down here. It says the rates of effusion of two gases are inversely proportional to square roots of their molar masses at the same temperature and pressure. Does this make sense to you? I sure hope so, because I talked to you in the last section saying that the heavier gases are slower and the lighter gases are faster. And so this is a way to describe this. So it says a rate is a change of quantity over time, not just the time, okay? So the rate of effusion of gas 1 divided by the rate of effusion of gas 2 is equal to, notice how the light gas, I'm going to make the light gas always gas 1. So notice it's an inverse. So the rate of the light gas is on top, the molar mass of the light gas is on the bottom. And if you do it that way, I think the numbers actually make more sense. So let's look at problem number 38. So it says calculate the ratio of effusion rates of hydrogen gas and uranium hexafluoride. So I put hydrogen gas on top because it's the light gas, and the rate of uranium hexafluoride is going to be on the bottom. But what is it equal to? It's equal to the square root of the flip. So put the molar mass uranium hexafluoride on top and the molar mass of hydrogen on the bottom. So when you do that, well, if you do the math, so look up uranium. It's like 230 something plus 6 times 19. Okay, you end up with 352. And then the molar mass of H2 is 2.02. And so when you get that, you get a number bigger than 1. You don't get a decimal number. All right, and when you actually take that value, you get 13.2. And so what does this 13.2 even mean? It means that hydrogen is 13.2 times faster than uranium hexafluoride per given quantity, okay? So if I want to evacuate, let's go back up to my picture, 10 molecules of hydrogen into here, it's going to be 13.2 times faster than evacuating, or I'm sorry, putting 10 molecules of uranium hexafluoride through that same pinhole over in here. Okay, so that's what that really means. So why don't you go ahead and at least start off doing the exact same thing in problem 39. They're asking a little different kind of a question. They're not just asking you for a ratio, but go ahead and do the same calculations, and then let's make sense of it. Are you paused? All right, welcome back. Well, this is what I got. Hopefully you did too. So I put the lightweight one, helium, on top, chlorine. So then I put the molar mass of chlorine, which is 70.9, divided by 4, which is the molar mass of helium, and I got 4.2. So I can make that same comment that helium is 4.2 times faster than chlorine, but that's not what they're asking for. They gave you some extra information. So if it took 4.5 minutes for helium to go through, all right, notice it's the same quantity, it's 1 liter in this case. How long does it take for the chlorine? Well, think about it. Who's going to go faster, helium or chlorine? Well, yeah, helium weighs less, right? So the time value needs to be bigger for chlorine. Well, how much bigger? Well, hopefully you got 4.2 times bigger. Okay, so how long did it take helium is 4.5. So 4.5 right up here minutes times 4.2 is 18.9 minutes. So does that make sense? Heavier chlorine is going to take longer to send its 1 liter through this pinhole than helium, okay? And then I wrote, no, helium lighter goes faster, chlorine heavier takes longer. So notice the time value for helium is 4.5. The time value for chlorine is 18.9. Those numbers are consistent, okay? Well, that was an awfully quick section. That's 5.9. We're done with that. So, hey, I'll just leave you with this. Don't wait to be great. See you next time. Bye-bye.